Jai Hind everyone. In this class, I'm going to discuss the topic active low pass filter of the subject integrated circuits. So in this class, I will discuss about active and passive filter first. After that, we'll discuss about the first order and second order active low pass filters. So starting with the filters. So firstly, we should understand that what is filter. So filter is a circuit which is used to pass a particular range of frequency and it blocks the other frequencies. That is not desirable, that is not wanted, right? So when I'm saying that it blocks the other frequencies, it means that those frequencies should be attenuated. So the function of the filter is to pass a particular frequency, range of frequency, and blocks the other frequencies, attenuates the other frequencies. So filters are classified into two parts. The first classification is analog and digital filters. See, analog filters, it performs the actions on the analog signal. It filters out the analog signals. It processes the analog signal. And digital filters also process the analog signals. But the difference between analog filters and digital filters is that digital filters process the analog signals using digital techniques. In this class, I am going to discuss the analog filter, right? That is to process the analog signals using analog techniques. Another classification of filters are active and passive filters. So active filters, as the name suggests, that the filter which utilizes active element like op-amp, right? In passive filters, there are only passive elements. It means that in passive filters, there are only three passive elements. These passive elements are resistor R, inductor L, and capacitor C. So the filter which is designed using only passive elements, that is R, L, C, those filters are referred as passive filters. And in case of active filters utilizes active element and it utilizes op-amp as an active element. But along with active element, there are passive elements also, and these passive elements are resistor and capacitor. So active filters are the filters which consist of op-amp as an active element. Along with op-amp, it contains two additional passive elements. These two elements are resistor and capacitor. So this is the just the component required to design active and passive filters. Now the next question arises that what are the advantages of active filters over passive filters? What are the advantages of passive filters over active filters? Like in network analysis, you people had studied passive filters. In those passive filters, you had used only resistor, capacitor, and inductor. There are advantages of passive filters as well as disadvantages also, limitations also. One of the advantage of passive filter is that it can be used for high frequency applications. High frequency means radio frequency. So we can use passive filters for radio frequency applications. But we don't use passive filters at low frequencies. We don't use passive filters at low frequencies. We don't use that. Low frequency, that is audio frequency. The reason is that at low frequency, the size of the inductors become very large. The size of the inductor becomes very large. You can see that the inductance, the impedance of the inductor is XL, that is omega into L, and L is equal to XL by omega. You can see that for high frequency applications, the size of the inductor will be less, but for low frequency, the size of the inductor will be large. That's why we don't use passive filters. Normally, we don't use for low frequency applications. And the main advantage of the passive filters is that it can be used for high frequency applications, that is radio frequency applications. But the disadvantage of passive filter is that we don't get gain using passive filter. Why we don't get any gain from passive filter? The reason is that passive filter consists of only passive elements, and with the help of passive elements only we cannot get gain. It means that there is attenuation in passive filter. That is one drawback. There is attenuation in passive filters. That is the first drawback. And the second drawback of passive filters is there is loading problem also in passive filters. And these two problems of passive filters are removed with the help of active filters. So this is very common question. That question is, what are the advantages of active filters over passive filters? What are the advantages of active filters over passive filters? So there are two advantages of active filters over passive filters. The first advantage is it provides gain. It provides gain. Active filters provide gain. Reason? Because in active filters we are using op-amp, and that can amplify the signal. And another advantage of active filters over passive filter is that there is no loading problem in active filters. Because when we use op-amp in filters, normally we prefer non-inverting configuration of op-amp. And for non-inverting configuration, the input impedance is very high, and that is very much desirable to reduce the loading problem. There is no loading problem. Fine. So these are the two main advantages of active filters. There is one limitation also of the active filter. That limitation is that the gain, bandwidth, product and slew rate of the active filters are limited by the op-amp itself. Reason? The reason is, since in active filters we are using operational amplifier, and that operational amplifier is having limited bandwidth and limited slew rate. If that op-amp is having limited bandwidth and limited slew rate, it means that when we design any filter with the help of that op-amp, it means that that filter will have limited bandwidth and limited slew rate. So the gain bandwidth product, that is also called unity gain frequency, and slew rate of the active filters are limited by op-amp. That is one limitation of active filters. So active and passive filters has its advantages and drawbacks. So as per the application, as per the requirement, we prefer active or passive filters. So mostly passive filters are used at high frequencies. So this is all about the an active and passive filter. In this class, we are focusing only on active filters. So next topic is types of active filters. Types of active filters. So there are mainly four categories. The first one is low pass filter, active low pass filter. Second one is active high pass filter. Third one is active band pass filter. Fourth one is active band reject filter. And apart from these four filters, there is one filter called KHN filter, that is also called referred as universal filters. With the help of KHN and universal filters, we can realize all the filters like low pass, high pass, band reject. And one more filter is there, that is called all pass filter. All pass filter is very much different from other filters. The reason is that it passes all the frequencies. As the name suggests, all pass. All pass filter, it passes all the frequencies, but it changes the phase of the input signal. Basically, all pass filter, it is used in transmission lines. So that is a different topic. So in this class, I am focusing on the first filter, that is low pass filter. So low pass filter, it is further classified into two parts. The first one is the first order active low pass filter, and the second one is the second order active low pass filter. Although there are third order, fourth order, fifth order active low pass filters also, but with the help of first order and second order filters, we can design high order filters. For example, if we want third order low pass filter,
So we can cascade the first order and second order. If we cascade first and second order, we get the third order low pass. Similarly, if we want fourth order low pass, so in that case, we can cascade two second order filters. If two second order filters are cascaded, then it becomes fourth order filter, right? So in short, we can say that with the help of first order and second order, we can design the higher order filter. So it is very important to understand the basics. That basics is first order and second order filter. And as far as first order and second order filters are concerned, the difference is only in the RC sections. As I mentioned that in active filters, we use resistor and capacitors also along with the op-amp. Op-amp, that is an active element, right? So in the first order filter, first order low pass filter, there is one RC section. It means that one resistor and one capacitor. And in second order low pass filter, there are two RC sections, means two resistors and two capacitors. Fine. Now coming to the active low pass filter. So starting with the first order active low pass filter. First order active low pass filter. So what will be the circuit? So let's take op-amp as an active element. This is operational amplifier. This is a symbol of operational amplifier. So as I have mentioned that when we design filters, active filters using op-amp, we prefer non-inverting configuration, because in non-inverting configuration, the input impedance is higher and it helps in minimizing the loading effect. So there is an input signal called Vin, and this Vin is the analog signal. Now we have to perform the filter operation on this input signal V. Fine. So to perform the filter operation, we connect one resistor R and one capacitor C. And the function of this RC section is to provide the filter operation, filter function, to provide the low pass filter function. And to provide the gain, as I have already mentioned, that is the advantage of active filters over passive filter. That advantage is it provides gain. And you have studied the non-inverting amplifier, right? In non-inverting amplifier, what we do, we apply the input signal at the non-inverting terminal, and at the inverting terminal, we connect a resistor R1, and there is a one feedback resistance, that is RF, and let's say output is V0. So this R1 and RF, it provides gain, and R and C, it provides the filter operation. Fine. So there are two operations that is there in this active filter. The one is the filter operation and another one is to provide the gain. To perform the filter operation, we connect this resistor and capacitor R and C, and to get the gain, we connect these resistors R1 and RF in negative feedback. Fine. So if we draw the frequency response of this first order low pass filter, frequency response means the variation of voltage gain in dB, voltage gain in dB with respect to frequency. So in low pass filter, as the name suggests, it passes the low frequency and attenuates the high frequency. When I say it passes the low frequency, it means that at low frequency the gain will be higher. And when I say that it attenuates it blocks the higher frequency, it means that it attenuates the higher frequency, means gain will be less at higher frequency. So the graph, the frequency response of the low pass filter will be like this. You can see that the maximum gain, let's say this gain is AF, and this AF is called passband gain, and this gain is decreasing. And for first order filter, this rate of decreasing of this graph, this gain is minus 20 dB per decade, minus 20 dB per decade. This is for first order filter, first order low pass filter. This is called roll off rate. And for the second order low pass filter, this roll off rate is minus 40 dB per decade. For third order low pass filter, the roll off rate will be minus 60 dB per decade. For nth order filter, For nth order filter, the roll-off rate will be minus n into 20 dB per decade, where n is the order of the filter. Now here there is one very important term called cutoff frequency. That cutoff frequency, let's say this is fh. This fh is the cutoff frequency. It is also called minus 3 dB frequency. It is also called break frequency. It is also called corner frequency, right? So it is the frequency at which the gain is reduced by 3 dB of the maximum gain. For example, if the maximum gain is 50 dB, so at fh the gain will be 47 dB. That's why cutoff frequency is also called minus 3 dB frequency. And there are two bands also. One is called pass band and another one is called stop band. So you can see that in the pass band the gain is higher and in the stop band the gain is decreasing. Fine. So this is the frequency response of the first order low pass filter. For the second order low pass filter, the roll off rate will be minus 40 dB per decade. Now we need to derive the transfer function, that is the voltage gain of this first order active low pass filter. So to derive the voltage gain, firstly just find out the voltage at the non-inverting terminal. Let's say this voltage is V1. Once we find out the value of V1, we can easily find out the value of V0, because we know the relation between V0 and V1, and that V0 is equal to 1 plus Rf upon R1 into V1, right? This is the gain of the non-inverting configuration. When we apply the input voltage at the non-inverting terminal directly, then the gain is 1 plus Rf upon R1 into V1. So for this circuit, what will be V1? That can be find out easily. So V1 will be equal to 1 by SC upon R plus 1 by SC into V. This is the value of V1. 1 by SC is, that is the impedance of the capacitor. Fine. Now put this value of V1 into this equation and calculate the value of V0. And after doing this, put S equal to j omega and further put omega is equal to 2 pi f. Fine. From there, just calculate the value of V0 upon Vin and take the mod. Then the value of V0 upon Vin, it will be equal to AF upon under root 1 plus F by FH whole square, where FH is the cutoff frequency, that is also called minus 3 dB frequency, and this FH is equal to 1 upon 2 pi RC. So this equation is important. V0 upon Vin, that is the transfer function, that is the voltage gain of the first order low pass filter. And when you derive for second order low pass filter, then in the equation there will be only one change. That change will be V0 upon Vin will be AF upon under root 1 plus F by FH to the power 4. For the third order low pass filter, it will be to the power 6. That is the only difference. Fine. So this is the transfer function and the cutoff frequency of the first order low pass filter. Now coming to the design of first order active low pass filter. So to design the first order active low pass filter, the step 1 is firstly mention the cutoff frequency FH. Normally in the numericals, FH is given. FH is the cutoff frequency. Then just take some value of C, and normally we take C less than or equal to 1 microfarad. Normally we choose the value of C such that the value of that capacitor should be available in the market. Fine. For example, you can choose 0.1 microfarad, 0.01 microfarad, 0.0047 microfarad. These capacitors are available. These fixed capacitors are available in the market. And after that, find out the value of R. So we can find out the value of R with the help of cutoff frequency equation. FH is equal to 1 upon 2 pi RC. FH from step 1, C from step 2. Here you can find out the value of R. Fourth step is find out the value of R1 and RF. For that, use the equation AF, that is equal to 1 plus RF upon R1. AF is pass band gain. See, in the previous slide, like FH I have mentioned, here the AF is the pass band gain and the value of AF is 1 plus RF upon R1. You can easily find out it. Just put V1 into that equation and just rearrange the terms. You will get this V0 upon V. Now, if in the question AF is given, then with the help of AF, you can find out the value of R1 and RF. but one equation, two unknowns. So normally we select R1 less than 100 kilo ohm. You can take the value of R1 any value, but normally it should be less than 100 kilo ohm. So AF is normally given in the question. R1 you will take some value less than 100 kilo ohm, and with the help of this equation you can find out the value of R1. And in the last step you will design the circuit and mention all the component values in that circuit. So these are the design steps for first order active low pass filter. Now just do one numerical, that is design a first order low pass filter with FH 1 kilohertz and pass band gain 2 and draw the frequency response also. Fine. So step 1, mention the cutoff frequency. In the question it is given FH is equal to 1 kilohertz. Step 2 is take some value of C. Let's say C is equal to 0.01 microfarad. Step 3, find out the value of R. For that use the cutoff frequency equation. FH is equal to 1 upon 2 pi RC. So from here R will be equal to 1 upon 2 pi FH into C. FH is given 1 kilohertz. C you have taken 0.01 microfarad. Now put all these values and find out the value of R. And in the fourth step, use the equation of pass band gain. AF is equal to 1 plus RF upon R1. Right? AF is equal to 2. In the equation it is given pass band gain. And let's say R1 is equal to 10 kilo ohm. Let's say R1 is equal to 10 kilo ohm. So what will be RF? From this equation, RF will be equal to R1, that is RF will also be 10 kilo ohm. And in the last step, just design the first order low pass filter that I have already discussed. So for that, step 5, again design the first order low pass filter. At the non-inverting terminal, we have connected a resistor and capacitor that forms one RC section, and this one is the input signal Vin. And to provide the gain, for that, at the inverting terminal, we are connecting a resistor R1, and in the negative feedback path, there is another resistor RF. Output is V0. So after designing this circuit, just mention the values of R1, RF, R and C. R1 that you have taken 10 kilo ohm, RF is we have got 10 kilo ohm, C we have taken 0.01 microfarad, and so R you can get it with the help of step 2 that you can calculate, right? R is equal to 1 upon 2 pi FH, 2 pi FH into C. Now put FH equal to 1 kilohertz, C is equal to 0.01 microfarad, and calculate the value of R and put that value R here. Fine. So this is the design steps for the first order low pass filter. And also in this question, you have to draw the frequency response also. So to draw the frequency response, although you have drawn the frequency response of the first order low pass filter, but in the numerical, to draw the frequency response, you have to make this table, and that table is the first column will be frequency. F is the frequency of the input signal. Then calculate the value of mod V0 upon Vin. Then convert this voltage gain into dB, because in the frequency response at the y-axis there is a voltage gain in dB. So in dB it will be 20 log mod V0 upon Vin. Fine. And we know the value of V0 upon Vin. We have derived it for the first order filter. It is AF upon 1 under root 1 plus F by FH whole square. That we have derived from here. This one. Right? AF upon under root 1 plus F by FH square. Fine. So everything is given in the question. AF is given, F is the frequency of the input signal, FH is given. So you need to take some values of frequency, and obviously you will take 1 kilohertz definitely, because 1 kilohertz is the cutoff frequency. So take few frequencies lesser than 1 kilohertz. Let's say 100 hertz, 500 hertz. Then similarly take few frequencies above cutoff frequencies. Let's say 1 kilohertz, 5 kilohertz, 10 kilohertz. Now this is the value of F, and with the help of this voltage gain equation, you can find out the value of V0 upon Vin. Further, with the help of calculator, you can find out that voltage gain in dB. And after completing this table, you will draw the frequency response that I have already discussed. That graph is between voltage gain in dB versus frequency. So obviously the graph will be like this. At low frequency, the gain will be high. At high frequency, the gain will be decreasing. So this is the method that how we solve the numerical problem based on first order low pass filter. Now coming to the second order filter, second order low pass filter, obviously active low pass filter. So in second order low pass filter, we require two RC sections. Two RC sections means like C. To provide the gain, what we do? At the inverting terminal, we are connecting a resistor R1, and in the feedback, that resistance is RF. Fine. And input signal is V. V is the input signal. This is R and C. Now see, if you apply this V at this RC section directly, then it becomes first order low pass filter, and it contains only one RC section, R and C, right? R and C. But in second order low pass filter, we require two RC sections. It means that we require two resistors. Let's say these resistors are R2 and R3, and two capacitors also. One capacitor is connected in the feedback path. Now V is applied at R2. And let's say these capacitors are C1 and C2. So you can see that this second order filter, it contains two RC sections, and these two RC sections are two resistors R2, R3 and two capacitors C2, C1. And these resistors R2, R3, C1, C2, it performs the filter function. And to get the gain, that gain is provided with the help of R1 and RF. That gain is provided with the help of R1 and RF. So see, this is the second order low pass filter. So when you derive the voltage gain of the second order low pass filter, then the equation is mod V0 upon Vin, that is equal to AF upon under root 1 plus F by Fh to the power 4. In the first order filter, what we have got? F by Fh square, but in second order, it is F by Fh to the power 4, where Fh is the cutoff frequency of the second order low pass filter, and Fh is equal to 1 upon 2 pi under root R2, R3, C1, C2. But for mathematical simplification, what we do, we take R2 equal to R3 equal to R, and C1 is equal to C2 is equal to C. And if we do it, then what will be the equation for Fh? It will be again 1 upon 2 pi RC. So normally we take R2 equal to R3 equal to R, C1 equal to C2 equal to C. So we get the cutoff frequency, same equation, 1 upon 2 pi RC. One more thing about second order low pass filter that is very important. That is the Butterworth response. Butterworth response means flat pass band. It means that when you draw the frequency response of the second order low pass filter, and at y-axis this is voltage gain in dB. The graph is like this. Now you see, this is the pass band which I have circled. So what we want flat pass band, means in the pass band the gain should be constant, the gain should be flat. To ensure the flat pass band in the second order filters, it is mandatory to put the value of AF is equal to 1.586. So the value of 1.586, this value of AF 1.586, it gives the flat pass band. And when we get the flat pass band, then we say that it is the Butterworth filter, it is the Butterworth response. So it is desirable to get the flat pass band. So for that, in the second order low pass filter, we put AF is equal to 1.586. It means that if in the numerical, the value of AF, that is the pass band gain, if the value of AF is not given in second order filter, then always take AF is equal to 1.586, because this value of AF ensures the flat pass band and which gives the Butterworth response. Fine. And obviously, this is the second order filter. So the roll off rate, it will be minus 40 dB per decade. Fine. So this is the circuit of second order filter. This one is the frequency response. Obviously, you can mention all things. This is the cutoff frequency FH. This one is the pass band. This one is the stop band. And the design steps for the second order low pass filter, it is same as first order low pass filter. Fine. There is only one difference, and that difference is the value of AF. We take AF is equal to 1.586, and obviously the equation of AF will be same. AF will be 1 plus RF upon R1 again, because in the second order filter also we are using non-inverting configuration. So the equation for AF will be same. The only difference between first order and second order is that the value of AF. In first order low pass filter, normally the value of AF is given in the first order filter. In the second order filter, we always take AF is equal to 1.586. Fine. So if I discuss about the design steps for the second order low pass filter, then again step 1 is mention the value of FH. Normally in the numerical FH is given. Step 2 is take some value of C, that C should be less than or equal to 1 microfarad. Since in the second order filter we require 2 capacitors, and for mathematical simplifications what we are doing, we are taking C1 is equal to C2 is equal to C. So you can take any value of C less than 1 microfarad, but normally choose the value of C such that that capacitor should be available in the market. Fine. For by doing this, it will be easier to design in the labs. Fine. Step 3 is find out the value of resistors, and there are 2 resistors, R2 and R3. Again, for mathematical simplifications, we are taking R2 equal to R3 equal to R, and by taking this C1 equal to C2 equal to C, R2 equal to R3 equal to R, again we are getting the cutoff frequency equation is equal to 1 upon 2 pi RC. Now FH is given, C you have taken, you can calculate the value of R, that R is equal to R2 equal to R3. Step 4 is to find out the value of R1 and RF. For that, again use the equation of AF, that is 1 plus RF upon R1. But here there is a difference. In second order filter, what we do, for Butterworth response for flat pass band, we are taking AF is equal to 1.586. Again, take R1 less than or equal to 100 kilo ohm. You can take any value, fine. You can take 5 kilo ohm, 10 kilo ohm, any value you can take, fine. So with the help of step 4, you can calculate the value of RF further. And in the last step, just design the second order active low pass filter and mention all the component values which you have find out from the step 2, 3 and 4. So these are the design steps of second order low pass filter. So if you have understood the first order and second order low pass filter, you can easily do the first order and second order high pass filter also. For example, this is the circuit of the first order low pass filter. To design first order high pass, what we do? We just interchange this R and C. We just interchange this R and C. If we interchange this R and C, it becomes first order high pass filter. In a similar way, to design second order high pass filter, just interchange these 2 resistors R2 and R3 with C2 and C1. It means that in place of R2 and R3, put C1 and C2, and in place of C2 and C1, place R2 and R3. By doing this, this second order low pass filter will become second order high pass filter. So once you understand the first and second order low pass filter, so it is very easy to understand the first order high pass and second order high pass. In high pass filter, we just interchange the resistor and capacitor. But remember that the R1 and RF will be same in both the filters, because the function of R1 and RF is to provide the gain, and the main filter function is performed with the help of R and C in the first order low pass filter and with the help of R2, R3, C1, C2 in the second order filter. But the role of R1 and RF, it is same in first order low pass and second order low pass. And that role of R1 and RF is to provide the gain. And that is the advantage of active filter over passive filter. That advantage is active filter provides gain. In passive filter, there is attenuation. That is the drawback of passive filters. Because in passive filter, there is no active element. If there is no active element, we cannot get the gain factor. Fine. And obviously, the second advantage that I have mentioned already in case of active filter, that is no loading effect. The reason is that we are using op-amp, and normally in the filter circuits, in active filter circuits, we prefer non-inverting configuration, and that advantage is higher input impedance. The advantage of non-inverting configuration is higher input impedance. Because of that, the loading effect is reduced. Fine. So this is all about the first order and second order low pass filter that I have discussed in this class. Thank you.